We're looking at exponential sequences. These are non-linear sequences. They're otherwise known as geometric. So this is where you'll have a sequence that's halving, doubling, tripling, quadrupling, and so on and so forth. So you have two examples here, 4, 8, 16, 32, 64. It's doubling every single time. This is halving every single time. So that's how I know they are exponential. This would be an exponential growth function because it's getting bigger and bigger and bigger. It'll grow towards infinity. This is an exponential decaying function because it's getting smaller and smaller and smaller. It's halving every single time, which means it's tending towards zero eventually. It'll never actually reach zero though, because of the fact that we keep halving the previous number to get the next number. Okay, in the following example, Orla is 8 meters away from a wall originally. She moves towards the wall, and with each move, she halves her distance between herself and the wall. Construct a table showing Orla's distance from the wall after each of her first 6 moves. So here's the table. Okay, when she's standing still, she hasn't made any moves at all yet. She is 8 meters from the wall. She takes 1 step. You half the distance that she originally was, so half of 8 is 4. Her second step, half of 4 is 2. Her third step, half of 2 is 1. Her fourth step, half of 1 is a half. Her fifth step, half of a half is a quarter. Her sixth step, half of a quarter is 1/8. So, and they're all in meters. You can write the fractions as decimals if you want. Okay. So they're all in meters. They are her distances from the wall after she takes each step. Plot the graph of Orla's distance from the wall against the number of moves she makes. Okay. So we have an XY axis. Her move or her step number is on the x-axis. So she was taking a total there of 6 steps. And the distance from the wall is measured in meters on the y-axis. So initially, she was 8 meters from the wall. So she hasn't moved anywhere. So 0 moves. She's 8 meters from the wall. After 1 move, she's now at 4. After 2 moves, she's at 2. After 3 moves, she was at 1. After 4 moves, she was at a half. After 5 moves, she was at 0.25, which is a quarter. And after 6 moves, she was at 1/8, which is 0.125. Plot those points and connect them, and you now see that you have a decaying exponential function. Okay, so it's getting smaller and smaller and smaller each time. But technically, she'll never actually hit the wall. Her distance from the wall will never actually be 0. Because you can't multiply a half, keep multiplying by a half, and ever end up with a 0 as your answer. So her distance from the wall will get minutely smaller. Okay, but it'll never actually equal 0. So there's her graph. Part 3 then said find a formula for her distance from the wall after n moves. So that means come up with a t of n formula. Now it's an exponential function, okay? So we could do out the table like this, but we'll do it manually to show exactly what was happening every time. So initially she's 8 meters from the wall. To get her next distance from the wall, we halved that. So we multiplied it by a half. To get her next distance, we multiplied this answer by a half again. That's the same as simplifying it and writing it using rules of indices. 8 times a half is the same as saying 8 times a half squared. Then to get her next distance from the wall, you multiply her previous answer by a half again. To tidy that up using rules of indices, a half by a half by a half is a half to the power of 3, multiplied by 8. To get her next distance from the wall, you multiply her previous answer, which is this, multiply that by a half again. And tidying that up, rules of indices, it'll be 8 times a half to the power of 4. So you can start to see a pattern, okay? When we had 1 move, there was a power of 1 on the half. When it was 2 moves, there was a power of 2. When there was 3 moves, there was a power of 3. When there was 6 moves, there was a power of 6. So for each of the move numbers, it equates to whatever power was on the half. So therefore, to come up with a t of n formula, t of n would equal 8 multiplied by a half to the power of n moves. Okay? That would be based off of this table. Now, you could use your t of n formula for a geometric sequence. But if you do that, term 1 is 0 moves. Term 2 would be 1 move. So just be careful if you are using your geometric formula for t of n. Alternatively, you do out your table by hand to show how would you get the next term, what was happening each time to be able to spot a pattern forming. Then the next question said, hence, so using what you just did, I just came up with a t of n formula. Find Orla's distance from the wall after 10 moves and give your answer in centimetres. Well, we were in meters, So we'll have to convert to centimetres and give your answer to the nearest centimetre. Okay, so we're using our formula for t of n, which we found up here, and we're looking to get t of 10. So sub 10 into the formula, get out your answer, but remember that's in metres. There are 100 centimetres in a metre, so all I have to do now is multiply that answer by 100 and you'll get 0.78125 centimetres. Round that to the nearest centimetre, they said, so that would be approximately 1 centimetre. So after 10 steps or 10 moves, she's roughly 1 centimetre from the wall at that stage. Okay, here's another one. I want you to try and do this question, pause the video and come back and correct your answer from the question. Okay, Tom lets go of a helium balloon inside an open-roofed sports stadium as he stands with it at a height of 1.5 metres from the grass. So he holds out his hand, he's holding this balloon, and his hand is 1.5 metres above the grass. Okay, so that's the original starting height of the balloon before he releases it. After every second that passes, the balloon's distance from the grass is going to triple. Okay, you assume there's no wind factor, so it's actually going to just fly vertically up into the air. It's not going to trail off in a certain direction. Okay, construct a table showing the balloon's distance from the grass after 4 seconds. Okay, so at a time of 0 seconds, the balloon is 1.5 metres from the grass because he's holding it in his hand still. Then he lets it go, and after 1 second, it's going to be triple the distance now. So I'm going to do up a table. Okay, these are the seconds, and this is the distance from the grass. So initially, no time has passed yet, he hasn't released it, 1.5 metres. Triple that, you'll get 4.5. Triple that, you'll get 13.5. Triple that, you get 40.5 metres, and triple that, you get 121.5 metres. So after 4 seconds, the balloon is 121.5 metres above the grass. Part 2 asks me to plot the graph of the balloon's distance from the grass against time in seconds. Okay, so on your x-axis is seconds, and on the y-axis it's going to be the balloon's distance from the grass. So all I'm doing now is I'm plotting that table that we just constructed there. Okay, so time is in seconds on the x-axis, go as far as 6 seconds. Distance from the grass, and we're measured in metres. So all I do now is I just plot those points. 0, 1.5. 1, 4.5, 2, 13.5, and so on. Okay, so I have all of the points plotted, connect them, and you have an exponential function. That is a growth function. It's going to continue on up to positive infinity because it's constantly tripling each time. As every second passes, it's tripling the distance from the grass. Part 3, find a formula for the balloon's distance after n moves. That means come up with the t of n formula. So I'm going to do out the table again, but I'm doing it by hand this time to figure out how would you get the distance from the grass. So initially it's 1.5 metres from the grass. Then I triple that answer. Then to get the next one, I would triple this answer. Okay, so it would look like this. 3 by 3 is 3 squared. For the next one, I would triple that answer. So again, 3 by 3 by 3 becomes 3 cubed. For the next one, I would triple the previous answer again to get the next one. 3 by 3 by 3 by 3 is 3 to the power 4. So you start to see a pattern. Okay. When it was 1 second, it was a power of 1. When it was 2 seconds, it was a power of 2. When it was 4 seconds, it was a power of 4. So when it's n seconds, it's a power of n. So n represents the seconds here for this one. Whereas if you want to use the geometric t of n formula, which is AR to the power of n minus 1, just remember if you use the geometric method, the geometric term formula, n would represent the term number, which means term 1 would be 0 seconds. Which is 1.5 metres. Term 2 would be at the first second. Term 3 would be at the second second. So it's important that you know what n represents if you used your geometric t of n formula instead of coming up with a pattern to see what your t of n formula would be. So here, n represents seconds. And part 4 says, hence, using what you just did, find the balloon's distance from the grass after 11 seconds. So n is going to be 11. Sub into that t of n formula and you'll get out 265,720.5 metres. Okay, so that's how far it is away from the grass after 11 seconds. Now, as I was saying, you could have used your t of n formula for a geometric series because all exponential sequences are geometric. So a would be your first term. A was 1.5 metres from the grass. The common ratio was tripling every time, so r is 3 to the power of n minus 1. Okay, so that would be your t of n formula, but in this instance, n represents the term number. It doesn't represent the number of seconds that have passed. It represents the term number. Okay, so that makes a difference. So for part 2, when it said, what distance would the balloon be from the grass after 11 seconds? Well, after 11 seconds, I'd be looking for term 12. And why? Because remember, term 1 was 0 seconds, term 2 was 1 second, term 5 would be 4 seconds, okay? So term 12 would be after 11 seconds. So now I sub 12 in instead of n, and I get out the same answer, okay? So that's the distance that the balloon would be away from the grass after 11 seconds, which was term 12. So you could do it that way as well. Okay, here's another question that I want you to do. So I want you to pause the video. Okay, go and do that question and then come back and correct it from the video afterwards. A ball is dropped from a height of 10 meters and it bounces back up to 6 meters. And then it bounces back up to 3.6 meters and so on. Draw a table and a graph representing the heights of the ball after the first 4 bounces. Okay. So, after no bounces, originally the height of the ball is 10 meters. Then it bounces, okay? And they said if it's dropped, it bounces back up to 6 meters. Right. After a second bounce, it bounces back up to 3.6 meters. So in order to figure out what's happening here, given that the ball is going to keep bobbing along until eventually it comes to a stop, well, I suppose in this regard, it's actually never going to stop. But I know in reality it would, okay? So this is an exponential function and it is a decaying function. The height of the ball is going to gradually get smaller and smaller and smaller as the ball keeps bouncing. Okay, so I want to know what height is it going to retain every single time. So it went from 10 meters down to 6. Okay, now remember, it's not linear. It's not going down by the same amount each time. It's definitely not linear. So it is a geometric sequence. So term 2 divided by term 1 would give you the common ratio. So 6 divided by 10 gives you the common ratio, or you could say term 3 divided by term 2. 3.6 divided by 6 gives you the common ratio as well. So when you do that, okay, term 2 divided by term 1, 6 over 10, breaks down to 3/5. So that means it bounced back up to 3/5 of its original height. Like 3/5 of 10 is 6. 3/5 of 6 is 3.6. 3/5 of 3.6 will give you 2.16. Okay, so it's bouncing back up to 3/5 of its original height. So basically it's losing 2/5 of its height on every single bounce, but it's going to retain 3/5, okay? So because it's going to help us to come up with the T of n formula later on, I start off with an initial height of 10 meters. After one bounce, I retain 3/5 of the height, so 10 by 3/5. After a second bounce, it would be your previous height, which was the 10 times 3/5, multiplied by 3/5 again, which becomes 10 times 3/5 squared. To get the next height, it's the previous height, which is this one, multiplied by 3/5 again, which tidies up to be 10 by 3/5 to the power 3. So you start to spot a pattern, okay? To get the T of n formula for the number of bounces, which is what they did ask me to come up with. So when it was the second bounce, it was a power of 2. When it was the fourth bounce, it was a power of 4. So when it's the nth bounce, it's a power of n. So that's my T of n formula, where n represents the number of bounces. Okay? If you would prefer to use your geometric T of n formula instead, which is AR to the power of n minus 1, A would be 10, common ratio is 3/5, so you'd have T of n is equal to 10 times 3/5 to the power of n minus 1. But here you'd have to state then that n is equal to the term number, because term 1 is 0 bounces, term 2 is 1 bounce, term 3 would be 2 bounces, term 5 would have been 4 bounces, and so on. So you could use your T of n formula for a geometric series, but just remember n then represents the term number. So if I wanted to get the 20th bounce, I'd be looking for term 21. If I wanted to get the third bounce, I'd be looking for term 4 instead, if I use that formula. Okay, so it just look like that instead. So remember, the term number is one more than the number of bounces. So term 5 would mean it's the 4th bounce. Term 20 would mean it's the 19th bounce. And it doesn't matter which T of n formula you give as long as you label what n represents in the question. Okay, So it wants me to draw the table done. So I've gotten all of the heights of the ball. Represent that on a graph. Okay, so the height is going to be on the y-axis, and on the x-axis it's going to be the number of bounces. Right, so number of bounces, and then the height of the ball that was retained in meters. So initially, remember, the height of the ball was 10 meters high. So it starts up here. It hasn't moved anywhere yet. It hasn't left my hand. It's up at 10 meters high. Then I drop the ball, so it's going to come down and bounce. So it's first bounce, and then it bounces back up to 6 meters of a height. Then it'll come back down, gravity brings it back down. It'll bounce for a second time, and it'll come back up to 3.6 meters high. So that's its height after the second bounce. Comes back down with gravity. Comes back down with gravity, hits the ground for a third time, bounces back up, okay, to, I can't remember what that height was, but it's just 2.16, I think it was. Comes back down with gravity, hits the ground, bounces back up again for a fourth time, and it's at a height, was it 1.2 or something like that? And obviously then the ball will come back down and hit the ground for a fifth time. Now it'll keep bobbing like that. Technically then the ball would never actually stop, but we know in reality it would. But that's my graph showing the height of the ball after each bounce. And we were doing it for 5 bounces. So that was, for 4 bounces anyway, right? So bounce back up to that final height after the 4th bounce. So just remember, to get the distance travelled after each bounce, the first time it bounces, it comes down a distance of 10 meters. But then when it bounces up to 6 meters, it has to bounce back down. So it travels the distance up and it travels the distance down here. It'll do the same for that one. It'll go up 3.6 meters, down 3.6. It'll go up 2.16 and down 2.16. And then after the 4th bounce, it'll just come up to there, because we only wanted to know after the 4th bounce what distance had it travelled, what height had it come back up to. So you would stop there, okay, unless you wanted to come back down and hit the ground for a 5th time. Okay, so everything labelled in green there is just showing you the distance that the ball would have travelled after each of those bounces. Because that will now help us with part 2. What is the total distance travelled by the ball after the 4th bounce? So back to my graph. It'll be 10 plus 6 plus 6. Plus 3.6 plus 3.6 plus 2.16, I think it was 2.16 anyway, plus another 2.16 plus whatever this one was, 1 point something. Okay, so you're just adding them together. But remember, the first one, it came down a height of 10 meters. It never went back up to 10 meters. So I'm only having 110. Then it bounced up 6 and down 6, so I doubled 6. It bounced up 3.6 and it bounced down 3.6. So that's 2 times 3.6. It came up 2.16 and down 2.16. So I double it. It came up 1.296 and down 1.296. So I double it. So I add then my total distance and I'm getting 36.112 meters. That is the total distance travelled by the ball after the 4th bounce. Okay. And again, remember, after that 4th bounce, the ball came up to the air, turned and came back down, and it sat on the ground. So you're assuming then, because they don't mention a 5th bounce, just assume that it stops and stands still after the 4th bounce then. Part 3, describe the type of series generated by the ball. Well, it's an exponential series, and it's a decaying exponential series because the height of the ball is going down and down and down. It's getting smaller and smaller and smaller. It's tending towards 0, but it'll never actually be 0, even though in reality we know the ball would stop bouncing. Okay, so exponential sequence, or you could call it a geometric sequence as well if you want. Part 4 of the question said, find an expression for the height of the ball after n bounces. Well, we've already done the work on that. The answer was t of n equal 10 times 3/5 to the power of n, where n represented the number of bounces. Okay, and it's important to note what n represents. Hence, using what you just did, find the height of the ball after the 8th bounce. Give your answer in centimetres to 2 decimal places. So remember, this was all expressed in meters to begin with. They want my answer to be in centimetres, so I'll have to convert at the end. So because t of n represents the number of bounces, okay, I want to get the 8th bounce, so it's going to be t of 8. So I'll sub 8 into that formula. I get out 0.1679616 metres. There are 100 centimetres in a metre, So just multiply that by 100 and you've now turned it into centimetres. They also want me to round it to 2 decimal places. So that means I will look at the 6. The 6 will mean the 9 has to turn into a 10. That means you add a 1 onto the 7. So 16.8 centimetres. After 8 bounces, the ball has bounced back up to 16.8 centimetres in height. Okay, here's another extra question to do. So I want you to pause the video again and go off and do this question. A rubber orb is dropped from a height of 27 metres onto a floor. So its initial starting height is 27 metres above ground, right? Each time it hits the floor, it's going to bounce back up to 2/3 of its original height. So it's going to retain 2/3 of its original height. It's losing 1/3 of its original height. Find the height on each of the first 4 bounces. So I'm going to set up a table. Okay, so it starts off, after no bounces, it was 27 metres high. After 1 bounce, 27 multiplied by 2/3, 18. After 2 bounces, it would be the previous answer multiplied by another 2/3, which would be 12 metres. Again, we want to eventually come up with the t-event formula. So it's 27 by 2/3 to the power of 2. To get the 3rd bounce, you'll multiply your previous answer again by another 2/3. So it'll become 27 times 2/3 cubed. That's 8 metres. To get the 4th bounce, it'll be this answer multiplied by another 2/3, which can be just written as 27 times 2/3 to the power of 4, which is 5.3 with a recurring decimal. So that's metres. So they are all the heights of the rubber orb after each bounce. Okay. Part 2 said find a formula for the height of the orb on the nth bounce. That means come up with your t-event formula. Right, spot the pattern. When it was a power of 1, when it was bounce 1, there was a power of 1 on the 2/3. When it was after 2 bounces, there was a power of 2. 3 bounces, there was a power of 3. 4 bounces, there's a power of 4. So therefore, after the nth bounce, it'll be 27 times 2/3 to the power of n, where n represents the bounces, the number of bounces, I should say. Hence, using what you just did, find the height on the 10th bounce. So sub 10 into that formula. And remember, my answer is in metres. Part 4. After how many bounces will the rubber orb be less than 0.21 metres high? So we're already in metres, so I don't need to convert. This was my t-event formula, okay, where n represents the number of bounces. And they said after how many bounces would that formula be less than 0.21 of a metre? So I'm going to let that expression, let it be less than 0.21. So I now have an inequality and I want to eventually solve for n. First thing I need to do is get rid of the 27. So I divide across by 27 on both sides. That will then leave me with 2/3 to the power of n is less than whatever this fraction would work out to be. Okay. So it becomes 7 over 900. You don't have to write it like that. You could just leave it as it was, but I will. Okay, you've got an unknown power in your index. So in order to solve it, you have to introduce logs. Because it's an inequality, the only log you're allowed to introduce is the natural log, ln. So I'm going to bring in a log with a base of e, ln, okay, the natural log, and what you do to one side, you must do to both sides of your equation. So I've gotten the natural log of the left is less than the natural log of the right-hand side. Then you apply your rules of logs. Bring down the power of n in front of the log, so it'll now look like that. N times ln 2/3 is less than ln 7 over 900. I want to get n on its own, so I need to get rid of the log of 2/3. So I'm going to have to divide across by the log of 2/3. But you have to check, is the log of 2/3 a positive or a negative number? Now, as a quick rule of thumb, the log of any proper fraction is always going to be negative. Whereas if that was an improper fraction, like a top-heavy fraction, well, then it would be positive. But you can just throw it into the calculator and check. So the log of 2/3 will be negative, which means when I divide across by the log of 2/3, I am dividing across by a negative number. And when you divide an inequality across by a negative number, that inequality symbol has to flip around. Okay, so n is now going to be greater than the log of 7 over 900 divided by the log of 2/3 into the calculator, and I'll get 11.977. So n has to be greater than that, and n would also have to be a whole number because n represented the number of bounces. I can't have 11.97 bounces. So if n has to be greater than 11.9, n must be 12, and it's bounces. So it took 12 bounces for the height of the rubber orb to be less than 0.21 metres in height. Okay, so that's our exponential sequences and series, otherwise known as geometric sequences and series.